Mr. Wizard.
Hi.
Why did you want me to bring my tape and my bike?
Well, this piece of tape that I asked you to bring is to go around your front wheel. So mount it at the front.
Okay.
And wrap it right around the tire and the wheel, the whole thing. Right through here, any old place.
Okay.
Okay. Now that's to mark that spot on the tire. Now put that spot on the ground.
Like that?
Yep. Now take a piece of wood and put it down there to mark it. Okay.
Okay.
Now go forward 1 revolution. Okay, now put the other piece down to mark it.
Okay.
Now, my question to you is, how far did the mark on the tire go?
Well, the length of the sticks, wouldn't it be?
You'd think so.
Yeah.
But it's actually a little more complicated than that. Come on, get on your bike, come on over to my house, I'll show you.
Okay.
Okay, Tarek, I have a challenge for you. I want you to pick up this stick like this, hold it, and now twist it.
Okay.
See? And you see, try it once. You should have no trouble, right? Now I'm going to add 1 kilogram of weight right here at that first screw eye. Now twist it again.
Okay.
What you have to do is try to lift that weight. You just barely got it off. Now, you see these little stripes that are along here?
Yes.
And notice there's a stripe across here too?
Yes.
Okay. This has all been designed so that the distance that you have to twist is the same as the distance from here to here.
Oh, okay.
And to define work, you say the mass, 1 kilogram,
Yes.
times the distance.
Oh.
This case is 1 to 1.
Okay.
That was relatively easy. Now I'm going to double the distance. Mass stays the same. Now give it a twist. Did it feel heavier?
Yes,
Why?
because it's 2 to 1.
Right. So you have to exert twice as much force over
Yes.
there. Here's 4 to 1. Now, it took a lot of it. Doesn't it
Yeah.
seem strange that the weight stays the same, yet it seems so much heavier? Now this is 8 to 1. You're going to have to exert 8 times as much torque. Twisting now. You're picking it up. Twist. Just barely. You just barely got it off. Okay, here's 16 to 1. Now, what is it you're going to have to do?
I have to twist it up.
You have to twist it, and you have to exert 16 times as much as this weight. All right, give it a try. Hard. Look at that. You can't even get it up off the table. That's because you've heard of the expression mechanical advantage? Probably not. That's when scientists or engineers are working with levers, they try to make them have a mechanical advantage. In this case, it's a mechanical disadvantage because I'm moving it further and further out. But you did very well. So let's move it back here where you can do it. What is it? You got 8, okay?
Yeah.
That's here. Okay, see if you can do 8. Twist! Twist! Come on! There you go. Congratulations, you got it. Alan, here's the problem for you. There's a washer and a card, and I'd like you to balance the washer on the edge of the card like that.
But it's impossible because the cardboard is too thin. Then
Well,
it'll
try
just...
it.
Okay. Try to put this in the middle. Can't do it.
Well, before you leave today, I will show you how to do it. First of all,
Okay.
fold the card. But now, obviously, you can balance it, right?
Yeah.
Like that.
Because
But
the support.
yeah, because there's support. But if you put the washer on the edge like that, and now slowly open the card, as you
Okay.
open it, the weight on one side is going to be greater, right? So there'll be more friction there, and there'll be less friction on the other side, so it'll move until the weight goes on that side.
Oh, so it's gonna switch because it's
switch
gonna
back and
have more
forth.
weight here and then over there.
Right, and if you
So-
do it just right, you can get it so that it's absolutely perfectly balanced.
See, it's switching right now.
Yes, it's switching right
and
now.
it's coming out.
Okay, get the idea?
Yeah.
Okay, you try.
Okay, sure. Okay, I'll put this washer at the corner.
Wait, now, but in this case, it's kind of rough on one side, so use the smooth side so that...
Okay.
You do it. I'm sorry, I don't want to...
Okay,
Your trick.
I'll do the
But use the smooth side. Turn it upside down.
smooth
There.
side. Okay,
Right.
put this at the corner.
Okay.
Now, slowly open it. And the weight is switching right now, so it's
Right.
coming out. And
So it's a magic trick that depends on friction,
Yeah.
right, and pressure. Okay, why don't you take it home and try it on somebody?
Great, I'll try it on my brother Albert. He
Well, good
loves
luck.
these.
Hope you can do it, and he won't. Okay.
Okay.
Aaron, here's a little plastic cup glued to this piece of wood.
Right.
It's a long piece hinged at the other end. Okay, here's the other piece down here.
Yeah.
Here's a little dot where I'm going to put this stick, and there's another little dot up here.
Oh, I see.
You see? Okay. Now, I gave you a steel ball. Would you put the steel ball on the T right there?
On the T.
Okay. Now, what I'd like you to do is to grab the stick out of the way. Go ahead.
Grab it out
Quick.
of the way?
Just grab it quickly and yank it out of the way.
What'll happen?
Go ahead.
Ball went in the cup.
Right. A magic trick based on a very sound scientific principle. See if you can figure it out. You go ahead, set it up again.
So you put the stick right on the dots,
There's the ball. Okay.
and you put the ball on the T.
Now, when you yank out the stick, the ball
Will
is
fall.
free to fall, right? It goes like this, okay?
Right.
But this stick is going to start to fall, but it's obviously has to beat the ball, right? Because that cup's got to get down here and the ball gets there.
Oh, yeah,
Right.
okay.
Think about this. Yank the stick out from under. Notice that
It all hits at the same
they
time.
all hit at the same time, right?
Right.
This means that if this part went at certain speed, this part has to go a lot faster.
To catch up to that far, because it's
That's
longer
why
distance.
I have this little record player. Notice the line there, the red
Yes.
dot and the green and the
Yeah.
blue dot. They're going at around at different speeds because they both end up right here at the same time, don't they?
The red dot's going faster.
They're going faster, right?
Yeah.
Okay. Now that's also true of this stick. Okay. Put it up again. Here we go.
Okay. Does the angle make any difference?
Yes, it does. If it were too steep like this, obviously, it would.
Oh.
And if it were down here like that, it wouldn't have enough time. So the angle is very important. I'm sorry. Go ahead. Fix it. Here, fix it up again. Okay. Here's the. Okay. So now you're going to do the magic trick and have gravity and free fall and angular momentum help you. When you yank the stick out, the ball is going right in the cup. Are you ready?
I'm ready.
Go. Beautiful. That may not look like it, Kelly, but that's a wishbone from a turkey.
How can you tie a bone in a knot?
Well, by treating it in a special way, and in fact, I'll show you how you can do that yourself. And when you try to make a wish with that, nobody gets it.
Yeah.
In fact, here's what you do. You soak a turkey or a chicken bone in this. Smell it.
Ooh, it's vinegar.
Yeah, it's vinegar. Here, now take the tongs and take out one of those great big turkey bones.
Okay.
Got it?
Yeah.
Okay, here.
There.
You can put it down on this tray. Okay. Now, here's what a turkey bone normally would be like.
Yes, it's hard.
Nice and hard. Now, the reason why it's hard is there are cells in here that contain calcium. That's what makes your bones hard, too, the calcium.
Yeah.
And when you put it in the vinegar, or you can put it in other kinds of acid, too, if you have them
Yeah.
around, why, then you dissolve away some of the calcium. So then it becomes like that.
It feels like rubber.
Yes. It's more like a tendon or sinew, you know, a sinewy
Yeah.
sort of tissue-like. Okay. Now, that's what happens to the big bones, and that would take, about a week. Here's one from a chicken.
It feels more rubbery.
Yeah. Okay, so here's the one that's the most fun. That's the wishbone. Here's a normal one. You making a wish? Okay. You got your wish. However, when you soak the bone in vinegar for a week or so,
You can tie it in a knot.
you can tie it in a knot instead of making a wish. There you go. Very good. Okay, you got your safety glasses on, all right?
Yeah.
I've got mine on. I'm turning this upside down and back and forth in order to mix something inside, and I have my thumb over a little hole.
Okay.
When I set it down on the counter there, you light the lighter and bring the flame near the hole.
Okay.
Okay? Are you ready?
Whoa!
You can see,
loud.
you can see why we have
Safety
nice light
glasses.
cups. They hit you right in the head.
Yeah.
Okay, well now you can take your safety glasses off. Because this is a sort of a, I call it an orange juice cannon because it's made out of orange juice cans, okay? And it's relatively simple and not particularly harmful, but because you're dealing with gasoline in the form of lighter fluid, you should do it only with your parents or in school with your teacher. So here's how to make one, however. Take a look at this because these are 3 cans taped together. Here's the bottom can.
Okay. That one, it's got a bottom but no top, and oh, there's the hole there.
There's the hole, see? There's the bottom, solid,
Yeah.
okay? Then here's the center can.
And that's got a bit of the top and the bottom.
Yeah, see,
Half
the
of the
partially,
bottom.
partially
Yeah.
cut out. That's to work as a baffle. So that's
Okay.
the center can, okay? Here's the top one.
And that one doesn't have anything in it.
Well, neither
It's just
top nor
hollow.
bottom. You put that on here and you tape them all together,
Right.
okay? Now, you then put lighter fluid in here and you mix it up like this, and that baffle that was in the center can helps mix the gasoline vapor and air to get a good mixture.
Okay.
And this is a good example of what happens inside your car thousands of times in a minute. The gasoline comes from the tank and air comes from the outside, and they're mixed by the carburetor and put into the cylinder. This is the cylinder,
Yeah.
right? Okay. Then when you have the right kind of mixture in it and everything's set to go, a spark plug sets it off. You're going to bring
The lighter,
the lighter
to the hole.
appeared near the hole. Then an explosion takes place that forces the piston, which is what this represents, push. Finally, the push goes to the wheels of your car and makes them turn around.
That's
okay?
neat.
So that's the idea. So now put on your safety glasses again,
Okay.
and we'll fire my orange juice cannon.
Okay. I need the
There's
lighter
that.
fluid.
Okay, some lighter fluid. So I caution you again, don't try this
Yeah.
at home except with your parents, because gasoline
Be dangerous.
or lighter fluid can be very dangerous when handled improperly.
Yeah.
Are you ready?
Yes.
Okay, see if you can not hit yourself in the head this time. Wait a minute. Fire. There, beauty. Okay, great.
What are these stakes stuck in the ground for?
Well, you'll see later, Shan, they're the answer to a very interesting mathematical puzzle.
Okay.
And here's this beginning of the puzzle. Here's an awl, you see what's stuck on the end of the tape? Stick it in front of the stakes in the ground there,
Okay.
because that's our starting point. And you'd take this tape and start off in that direction and run it around the entire Earth.
I have to go to school tomorrow.
Then we better get going right away, quick. So come on, keep going, as though we were going all the way around the Earth. Okay, that's far enough in this direction. Now put it down. Now come back and we'll meet the tape coming in the other direction. Okay, pick the tape up there,
Okay.
and now go back to where we started. Okay, now we theoretically have put this tape around the entire circumference of the Earth. Okay,
Right.
I have calculated for you some various things. You know what this stands for?
Circumference equals diameter times
Pi. Okay, and here's the diameter of the Earth in meters.
12,742,400 meters.
Okay, therefore the circumference is,
40,011,136 meters.
okay, this 136, very important. Keep that in
Okay.
mind, because what we are going to do is assume, here you take one end, I'll take the other. We assume that we're going to add 1 meter to the circumference of the Earth.
Okay.
And the question is, how high would it be off the ground? The level of this stake like that, the level of that stake, or the level of this stake?
I don't know. I'll guess the middle one.
You guess the middle simply because it's the middle?
Yeah.
Okay. Let's figure it out mathematically.
Okay.
Remember I pointed out the circumference here was ended up in 136?
Right.
See the new circumference?
40,011,137.
We've added 1 meter, right?
Right.
Okay, therefore, this is the new diameter.
12,742,400 0.31 meters.
Okay, that's 31 centimeters, right?
Right.
And the diameter, what would the radius be?
15.5.
Half that.
Right.
Okay, which stake is that?
Must be this one, I think.
Well, here is the meter that we added.
Right.
And here's 15 centimeters right here. See it? It's that
Yeah.
one. So here, you take that in. I'll take this. Put it there. Too low. Hold up a little higher. Come on, don't, because that's going to be that way all the way around the entire circumference of the Earth.
That's amazing.
Isn't it?
Except it doesn't seem like it's right, but we just figured it out.
Right. And we did it before school tomorrow, too. Christina, you recognize these, I assume?
Yeah, they're carnations.
Yes, and you can buy them at a flower shop.
Yeah.
They're usually available all year long, grown in greenhouses. And you can do some very nice scientific experiments with it, based on the fact that inside these little stems are tubes that the water gets up to the blossom. But you must be careful when you cut off the stem, that you do it at an angle underwater with a very sharp tool like a razor blade, so be very careful. And the reason you do that is you don't want little air bubbles to get caught in the ends of the tubes, then the water can't get up there.
And then I'll kill the flower.
Yeah, and then they'll wilt.
Yeah.
So after you've done that, then you can add food coloring to the water. And this is what happens sort of overnight.
Blue.
Isn't that nice?
Carnations blue.
Yes, they've made a little blue fringe.
Yeah. It's pretty.
Okay, what's your school color?
Blue and green.
Well, we got half of it, right?
Yeah.
The blue. How about these?
It's a red flower and a green flower.
There's the green and red.
But this is mixed up, green and
Yeah.
red.
Well, why do you suppose that's green and red?
Well, because you cut the stem in half and the red water goes in this tube and makes this
Right.
side red. And then the green water goes in here and makes this side
Now
red.
you said cut in half.
Yeah.
Not quite, right?
Okay.
There's a little more red than the green, so I didn't cut it quite in half.
Little
But
uneven.
now you can combine these two, and you'd have your school colors.
Yeah.
So when you have a party next time, all you need is white carnations, food coloring, and cut it off at an angle with a sharp instrument, and you can make your own school-colored carnations. Imagine what it would be like if the winter lasted a little longer than usual. Then the following year, the winter was longer yet. Each year, the cold would continue to last longer until finally the snow and ice remained on the ground all year round. This actually happened several times during the Earth's history and is called an ice age. The last one ended only about 40,000 years ago. More than 1/3 of all the land on Earth was covered by a great sheet of ice and snow. In this hemisphere, it stretched from the North Pole, covering almost all of Canada and extending far down the Mississippi Valley. From fossil records, scientists estimate the ice over Canada was over 3 kilometers or 2 miles thick. As the snow and ice continued to accumulate, it formed glaciers, similar to those still found in parts of Canada and the United States. Eventually, the glaciers moved down slowly over the land. The force of such giant packs of ice and snow is hard to imagine. They were powerful enough to gouge out the Great Lakes and thousands of smaller lakes all across the continent. Scientists have developed theories to explain the cooling of the Earth that led to the beginning of an ice age. A change in the energy output of the sun. A volcanic eruption that produced a huge cloud that blotted out the light from the sun. Even a change in the Earth's orbit around the sun. During the last ice age, man was a nomadic hunter who could move further south to escape the year-long winter. Some scientists believe another ice age is not an impossibility. It could be important to our future to continue to explore what can trigger such a drastic change in the climate and consider what can be done should conditions develop that could lead to another ice age. You know, this can represents your bike wheel.
Okay.
And this pen that I have spring mounted here represents the mark we put on the bottom. See where the bike wheel was touching the ground?
Yeah.
Okay. So now I'm going to put a mark here where we started. That's
The
sort
axle?
of opposite the axle, right?
Yeah.
Okay. Now I'm going to put the pen down so we make a mark starting at that point.
Okay.
Just like that. Okay, now I'm going to roll the bike forward. Watch what happens. Now I'll make another mark where we finished. Okay, now this board comes out.
Oh, okay.
Put the top on there, and now let us put this chain to mark the path of the mark on the wheel. Okay, about like that. Okay. Okay, now move it to where the axle began. And look how much extra.
Oh,
You
yeah.
see? Now you see why I said the bike wheel goes further than you do? What happened to it?
Well, the bike wheel started to come up under the line,
Right.
and then came over the line, and then went back under.
Right. So now let's try the same thing with your bike.
Okay. Okay, so there the tape is on the ground,
Okay.
and then it comes up, way up, over the axle or the line, and then it's back down on the ground. So that means that the tire, or the bicycle tire, goes farther than the bicycle itself.
Yeah, and further than you, too. Very good. Okay.
What was that, Mr. Wizard?
Well, that was a little explosion. And now you can take your safety glasses off. What I had on the water there was an element called sodium. First of all, do you know what an element is?
Well, isn't an element what everything is made out of?
Yeah, everything is made up of the somewhat over 100 elements. And the common ones that you know are carbon, aluminum, iron, things like that. And that was sodium.
Okay.
That I put on the water. And it's a very interesting chemical because it's half of table salt. Do you know what table salt, the formula for the chemical name?
Isn't it
Sodium chloride. Right,
yes.
sodium chloride. Well, there are two poisons put together to make something that we sprinkle on food, and there is half of it right there, the sodium. Now, the reason I wanted to show it to you is because, first of all, it's very dangerous, so that you can't do it ordinarily. So either your teacher does it or something. And you can't buy it. You got to get it at a chemical supply house. Because as you can see, once you put it on water, it yanks away the oxygen and hydrogen from the water to form sodium hydroxide and releases hydrogen. That's what makes it skirt around on the water like that.
Okay. What is the pink?
Well, I put an indicator in the water, so whenever it creates sodium hydroxide, it turns that red color.
Okay.
So let's try it again. I'll put on a little bigger piece, see if we can get another explosion.
Okay.
And you see why we have safety glasses on?
Yes, I do.
So don't worry, you can't do this at home. That's one of the reasons I'm doing it for you, okay?
Okay.
All right, a little bigger piece this time, and stand back as we see what happens when the element sodium contacts water.